Welcome back. In the last video, we did something super exciting. We trained our model for 100 epochs and look how good the predictions got. But I finished it off with challenging you to see if you could align the red dots with the green dots. And it's okay if you're not sure how the best way to do that. That's what we're here for. We're here to learn what are the best way to do these things together. But you might have had the idea of potentially training the model for a little bit longer. So how could we do that? Well, we could just rerun this code. So the model's going to remember the parameters that it has from what we've done here. And if we rerun it, well, it's going to start from where it finished off, which is already pretty good for our data set. And then it's going to try and improve them even more. This is, I can't stress enough, like what we are doing here is going to be very similar throughout the entire rest of the course for training more and more models. So this step that we've done here for training our model and evaluating it is seriously like the fundamental steps of deep learning with PyTorch, is training and evaluating a model. And we've just done it. Although, albeit to predict some red dots and green dots, that's all right. So let's try to line them up, hey? Red dots onto green dots. I reckon if we train it for another 100 epochs, we should get pretty darn close. You ready? 3, 2, 1. I'm going to run this cell again. Runs really quick because our data is nice and simple. But look at this. Loss, we start at 0244. Where do we get down to? 008. Oh my goodness. So we've improved it by another 3x or so. And now this is where our models got really good. On the test loss, we've gone from 0.0564 and we've gone down to 0.005. So almost 10x improvement there. And so we make some more predictions. What are our model parameters? Remember the ideal ones here. We won't necessarily know them in practice, but because we're working with a simple data set, we know what the ideal parameters are. Model 0 state dig weights. These are what they previously were. What are they going to change to? Oh, would you look at that? 06990. Now, again, if yours are very slightly different to mine, don't worry too much. That is the inherent randomness of machine learning and deep learning. Even though we set a manual seed, it may be slightly different. The direction is more important. So if your number here is not exactly what mine is, it should still be quite close to 0.7. And the same thing with this one. If it's not exactly what mine is, don't worry too much. The same with all of these loss values as well. The direction is more important. So we're pretty darn close. How do these predictions look? Remember, these are the original ones. We started with random, and now we've trained a model. Oh, so close. So close to being exactly that. So a little bit off, but that's all right. We could tweak a few things to improve this, but I think that's well and truly enough for this example purpose. You see what's happened. Of course, we could just create a model and set the parameters ourselves manually, but where would be the fun in that? We just wrote some machine learning code to do it for us through the power of backpropagation and gradient descent. Now, in the last video, we wrote the testing loop. We discussed a few of the steps here, but now let's go over it with a colorful slide, hey? Because, I mean, code on a page is nice, but colors are even nicer. Oh, we haven't done this. We might set up this in this video too. But let's just discuss what's going on. Create an empty list for storing useful value. So this is helpful for tracking model progress. How about we just do this right now, hey? We'll go here and we'll go. So what did we have? Epoch count equals that. And then we'll go loss values. So why do we keep track of these? It's because if we want to monitor our model's progress, this is called tracking experiments. So track different values. If we wanted to try and improve upon our current model with a future model, so our current results, such as this, if we wanted to try and improve upon it, we might build an entire another model and we might train it in a different setup. We might use a different learning rate. We might use a whole bunch of different settings. But we track the values so that we can compare future experiments to past experiments, like the brilliant scientists that we are. And so where could we use these lists? Well, we're calculating the loss here, and we're calculating the test loss here. So maybe we each time append what's going on here as we do a status update. So epoch count dot append, and we're going to go the current epoch, and then we'll go loss values dot append the current loss value, and then we will do test loss values dot append the current test loss values. Wonderful. And now let's reinstantiate our model so that it starts from fresh. So this is just create another instance. So we're just going to reinitialize our model parameters to start from 0. If we wanted to, we could functionize all of this so we don't have to go right back up to the top of the code. But just for demo purposes, we're doing it how we're doing it. And I'm going to run this for, let's say 200 epochs, because that's what we ended up doing, right? We ran it for 200 epochs because we did 100 epochs twice. And I want to show you something beautiful, one of the most beautiful sites in machine learning. So there we go, we run it for 200 epochs. We start with a fairly high training loss value and a fairly high test loss value. So remember, what is our loss value? It's MAE. So if we go back, yeah, this is what we're measuring for loss. So this means for the test loss, on average, each of our dot points here, the red predictions, are 0.481. That's the average distance between each dot point. And then ideally, what are we doing? We're trying to minimize this distance. That's the MAE. So the mean absolute error. And we get it right down to 0.05. And if we make predictions, what do we have here? We get very close to the ideal weight and bias. Make our predictions. Have a look at the new predictions. Yeah, very small distance here. Beautiful. That's a low loss value. Ideally, they'd line up, but we've got as close as we can for now. So this is one of the most beautiful sites in machine learning. So plot the loss curves. So let's make a plot, because what were we doing? We were tracking the value of epoch count, loss values, and test loss values. Let's have a look at what these all look like. So epoch count goes up, loss values ideally go down. So we'll get rid of that. We're going to create a plot, plt.plot. We're going to step back through the test loop in a second with some colorful slides. Label equals train loss. And then we're going to go plot. You might be able to tell what's going on here. Test loss values. We're going to visualize it because that's the Data Explorer's motto, right? Is visualize, visualize, visualize. This is equals... See, Colab does this autocorrect that doesn't really work very well. And I don't know when it does it and why it does it. Have we got... Oh no, we didn't say loss value. So that's a good autocorrect. Thank you, Colab. So training and loss and test loss curves. So this is another term you're going to come across often, is a loss curve. Now you might be able to think about a loss curve. If we're doing a loss curve and it's starting at the start of training, what do we want that curve to do? What do we want our loss value to do? We want it to go down. So what should an ideal loss curve look like? Well, we're about to see a couple. Let's have a look. Oh, what do we got wrong? We need to, turn it into NumPy. Is this what we're getting wrong? So why is this wrong? Loss values, why are we getting an issue? Test loss values. It's because they're all tensor values. So I think we should, I might change this to NumPy. Oh, can I just do that? If I just call this as a NumPy array, we're going to try and fix this on the fly, people. NumPy array. Will this turn this into a NumPy array? Let's see if we get NumPy. We're figuring these things out together. NumPy as NumPy. Because matplotlib works with NumPy. Yeah, there we go. So can we do loss values? Maybe I'm going to try one thing, torch.tensor, loss values, and then call CPU.numpy. See what happens here. There we go. Okay, so let's just copy this. So what we're doing here is our loss values are still on PyTorch, and they can't be because matplotlib works with NumPy. And so what we're doing here is we're converting our loss values of the training loss to NumPy. And if you recall from the fundamentals section, we call CPU and NumPy. I wonder if we can just do straight up NumPy. Because we're not working on the... Yeah, okay. We don't need CPU because we're not working on the GPU yet, but we might need that later on. Will this work? Beautiful, there we go. One of the most beautiful sights in machine learning is a declining loss curve. So this is how we keep track of our experiments. Or one way, quite rudimentary. We'd like to automate this later on, but I'm just showing you one way to keep track of what's happening. So the training loss curve is going down here. The training loss starts at 0.3, and then it goes right down. The beautiful thing is they match up. If there was a too big a distance behind the train loss and the test loss, or sorry, between, then we're running into some problems. But if they match up closely at some point, that means our model is converging and the loss is getting as close to zero as it possibly can. If we train for longer, maybe the loss will go almost basically to zero. But that's an experiment I'll leave you to try, to train that model for longer. Let's just step back through our testing loop to finish off this video. So we did that. We created empty lists for strong useful values, storing useful values, strong useful values. Told the model what we want to evaluate, or that we want to evaluate. So we put it in an evaluation mode. It turns off functionality used for training, but not evaluation, such as dropout and batch normalization layers. If you want to learn more about them, you can look them up in the documentation. Turn on torch inference mode. So this is for faster performance. So we don't necessarily need this, but it's good practice. So I'm going to say that, yes, turn on torch inference mode. So this disables functionality such as gradient tracking for inference. Gradient tracking is not needed for inference, only for training. Now we pass the test data through the model. So this will call the model's implemented forward method. The forward pass is the exact same as what we did in the training loop, except we're doing it on the test data. So big notion there, training loop, training data, testing loop, testing data. Then we calculate the test loss value, how wrong the model's predictions are on the test data set, and of course, lower is better. Then finally, we print out what's happening so we can keep track of what's going on during training. We don't necessarily have to do this. You can customize this print value to print out almost whatever you want because PyTorch is basically very beautifully interactive with pure Python. And then we keep track of the values of what's going on in epochs and train loss and test loss. We could keep track of other values here, but for now we're just going, okay, what's the loss value at a particular epoch for the training set and for the test set? And of course, all of this could be put into a function, and that way we won't have to remember these steps off by heart. But the reason why we've spent so much time on this is because we're going to be using this training and test functionality for all of the models that we build throughout this course. So give yourself a pat on the back for getting through all of these videos. We've written a lot of code, we've discussed a lot of steps, but if you'd like a song to remember what's happening, let's finish this video off with my unofficial PyTorch optimization loop song. So, for an epoch in a range, call model.train, do the forward pass, calculate the loss, optimize a zero grad, loss backward, optimize a step, step, step. Note you only have to call this once, but now let's test. Call model.eval with torch inference mode, do the forward pass, calculate the loss, and then the real song goes for another epoch because you keep going back through. But we finish off with print out what's happening. And then, of course, we evaluate what's going on. With that being said, it's time to move on to another thing. But if you'd like to review what's happening, please, please, please try to run this code for yourself again and check out the slides and also check out the extra curriculum. Oh, by the way, if you want a link to all of the extra curriculum, just go to the book version of the course and it's all going to be in here. So that's there ready to go. Everything I link as extra curriculum will be in the extra curriculum of each chapter. I'll see you in the next video.